Welcome. When we start in univariate statistics, we work with one vector, where each xi is a scalar value. We can describe its data with its measures and make inferences from its statistics to the population parameters. Here, in multivariate statistics, which is what we mostly work with in real life, we now work with multiple vectors x and y. The x1s are called independent variables, features, or predictors. These together form a matrix X. In addition, we work with one or multiple vectors y. These are also called dependent variables, target or response variables. Same as in the univariate world, we also describe its data with its measures, being one vector only, and relationships between multiple vectors, such as covariance or correlation. We make inferences from its statistics to the population parameters, but now we use what we call multivariate distributions or joint distributions. We make classifications and regressions. These are relationships between x and y. When it's a binary outcome that you are interested in, it's called classification. When it's a continuous outcome, it's a regression. As for distributions, same as before as in univariate statistics, we use distributions as black boxes to yield a probability. All we need to ascertain is the type of problem, and with it, if the variable is categorical or continuous. Here, just as before, if our vector is categorical or continuous, it will then follow a categorical distribution, multinomial, a generalization of the binomial distribution, and with its single case as well, but here it is called multinulli, a generalization of the Bernoulli distribution. Or, when it's the continuous distribution case, we have these options: the multivariate normal distribution, the multivariate student t distribution, the Wishart distribution, and the Dirichlet distribution. In multivariate statistics, we now do much more linear algebra matrix operations math, but the concepts are the same. One note, it's important to know how to do these exercises by hand using smaller matrices, but then, contrary to the academia folks, it's completely unpractical in the real world. We just use computers instead. So let's continue. By convention, in multivariate statistics, we use x and y vectors as columns, like this. Similar concepts as before, but with adjusted formulas. As for the mean vector, the covariance matrix, note here specifically we use the capital sigma or S symbol to denote the covariance matrix. It's not the sum. And the standard deviation matrix. Same as before, we just do the square root of the diagonal elements of the covariance matrix. In multivariate statistics, we also introduced the concept of the quadratic form. A can be the covariance matrix or a variation of it, inverse convariation matrix, or some transformation of it. This expression will yield a vector. Yx transposed and x. When we apply x transposed by A, we get vector x. When we then multiply it by x, we get a scalar value. Why is this important? Quadratic forms are important because they provide a way to represent and analyze relationships between variables in a multidimensional space. We also do transformations. We can do linear quadratic transformations of the vectors to preserve normality, and matrix partitions, if we are interested in working with a subset of a larger matrix. Here we also introduce the concept of dimensionality reduction, meaning if we are interested into trying to make an assessment on y vector from the x matrix, and if there is a way for us to simplify a matrix in a different dimension representation. These are the main methods. As for the linear ones, we have principal component analysis, linear discriminant analysis, singular value decomposition, and factor analysis. As for the non-linear main methods, we have uniform manifold approximation and projection, t-distribution stochastic neighbor embedding, and autoencoders. In multivariate statistics, we often deal with distances. In univariate statistics, the distance is straightforward to calculate. We use it as part of when we are interested in checking differences between observed and expected values. But here, we now need a more robust way to do that. There are two ways: the Euclidean, which is an extension of the univariate space, and the Mahalanobis distance. This is more used because it normalized the data. This will be used as a standard in hypothesis testing, where we want to check if mu1 belongs to a confidence ellipse, meaning if it is significantly different from mu0. As for inferencing, we do inferencing as well, but there are new concepts to learn now. As for hypothesis tests, same concept but with vectors instead. We use Oettling's t-square and analysis of mean vectors. This is an extension of the student's t-test to the multivariate domain. It can be done with one sample, two independent samples, and paired samples. We use ANOVA, repeated measures ANOVA, analysis of covariance, multivariate ANOVA, repeated measures MANOVA, multivariate ANCOVA, and canonical correlation analysis. We'll do lots of exercises on these in future videos. As for test statistics, we have 4 new concepts to learn. Wilks, it tests hypotheses about multivariate means. Pillai measures the proportion of variance explained between groups. Oettling-Lawley, which is an extension of the Oettling's t-square, and Roy, which tests the largest eigenvalue of the hypothesis matrix test for group differences. We also use the concept of Benforini correction. This correction lowers the confidence interval for more conservative assessments. As for confidence intervals, instead of confidence interval, we now use confidence ellipse. It highlights a region instead of an interval. Its centroid is the mean vector of that region. It's usually plotted with an associated confidence rectangle, which is just a perimeter box around the ellipse with a line for better visualization. One note on graphics. Besides all graphs we use in univariate statistics, like box plots, histograms, and so on, we still use these here, but sometimes combined, like this one. We also used 3D scatter plots. This is why computers come to aid, which helps us in visualization. And we also have new graphical concepts such as biplots. These combine information from principal component analysis and scatter plots, and heat maps. These show data intensity through color gradients. This is useful for visualizing the magnitude of relationships in matrix data or correlations. And that's it for this video. This is a quick introduction to multivariate statistics, but it is a key important step so you don't get sidetracked with math without getting the idea. In future videos, we'll go through all these in much more detail, doing lots of exercises.